if I told you the device silent power in your home has no moving parts, transfers millions of watts of electricity with over 98% of efficiency. From the basing pole-mounted unit on your street to the massive substation, giants transformers are everywhere. They do not just move power, they make modern life possible. In this video, we will dive into how transformers really work, from the electromagnetic induction to winding structures, oil cooling, and voltage control. Let us unlock the core of power transmission. Why transformers exist? Electricity is generated far from where it is used. Power plant may be hundreds of kilometers away from your home, but transferring that power efficiently, that is where transformers come in. Here is the challenge. Transmitting electricity at low voltage means high current, and that means huge energy loss due to heat. But if we step up the voltage, we can reduce a current and minimize the loss. And at the user end, we simply step it back down for safe. This ability to shift voltage level without energy conversion is what made AC power transmission practical in the late 19th century. The principle electromagnetic induction. At the heart of transformer is one elegant law of physics, Faraday's law, electromagnetic induction. When you move a magnet near a coil, a voltage is induced. Why? Because the magnetic flux linking the coil is changing. So if we apply alternating current AC to a coil, the magnetic field around it is constantly changes. If a second coil is nearby, this changing magnetic field induces a voltage in it. This is called mutual induction, and it is the core principles of transformer operation. But iron is not a great magnetic conductor. Most of the magnetic field will leak, so we insert an iron or steel core between the coils to channel the magnetic flux efficiently. Basic structure. A typical transformer has a primary winding connected to input, a secondary winding connected to load or output, a ferromagnet laminated core between them. The voltage ratio between a primary and a secondary is set by the number of turns in each coil. More turns on secondary means step up transformer. More turns on the primary means step down transformer. But when a magnetic field passes through a metal, they induce a small unwanted currents, eddy currents, which causes a heat loss. That is why the core is laminated, made from a thin insulated steel sheets stuck together. This breaks up the loops and significantly reduces loss. So even with a millions of watts flowing, a power transformer often reaches efficiency over 98% to 99%. Cooling and oil system. Transformers get hot, really hot. To manage the heat, all the internal are submerged in insulating mineral oil. This oil performs two critical functions. Number one, cools the windings and core. Number two, electrically insulates the internal components. As the oil heats up, it expands, so we use a conservative tank connected to the main transformer body. This tank adjusts for the oil volume changes and keeps air out, preventing moisture and oxidation. Types of transformers. There are two major structural types. Core type transformer, winding are around the core line limbus. Shell type transformer, core surrounds the windings. The working principle is the same. The choice depends on the voltage level, the cost, the cooling, or mechanical stress. Smaller transformer like the one outside your house step voltage down from 11 kilovolt to 220 volt or 120 volt. A large three-phase transformers handles hundreds of megawatts in industrial and grid-scale applications. Thus use a star delta connection, special paper insulation, and custom winding arrangement like helica and continuous disc, all engineered for long life and extreme power loads. Pushing and external connections. Electricity has to enter and exit the transformer safely. That is where pushing comes in. There are two types. Low voltage pushing, often plane based. High voltage pushing use oil impregnated condenser layers for smooth voltage grading and insulation. These pushing are carefully engineered to withstand electrical stress, environmental conditions, and even lighting strip. Voltage control, tappings. Even after installation, transformers may need fine-tuning. That is done with tappings, connection points on the winding that changes the effective number of turns. Large transformers use on-load tap changers, which adjust the voltage while the transformer is operating. Voltage control, tappings. Even after installation, transformer may need fine-tuning. That is done on tappings, connection point on the winding that changes the effective number of turns. Large transformer use on-load tap changers, which adjust voltage while the transformer is operating without interrupting the load. Taps are usually placed on the high voltage side since it is easier to insulate, current is lowered, switching easier. The tap changer is operated by a motorized drive system and it is housed within the main celled transformer tank. So now you know a transformer doesn't rotate, it doesn't convert energy, but it transforms lives silently and efficiently, managing power across the globe from your home to entry cities. This device are the heartbeat of modern power system. Thank you for watching this video. Like and subscribe. Join the Phantom Tedious community where engineering comes alive.